started with our last talk for today. We have Anand who's going to take the stage with getting into performance, and he's going to talk about Jasper and data science.
Everyone. So, how many of you have used Jupyter notebooks? Oh, nice. So, today's talk is about it's a story of like how I built this open source tool Jasper. Like I started building it in last year in around June and built it, and now the project has around 14,000 users. So I'll tell you this story, like how I built this. Yeah. So I'm based in Hyderabad, and these are my uh, where you can find me. And let's talk about the PyData stack. So in PyData stack, we have Python to the core, and we have various libraries around it, like linear algebra, machine learning libraries, plus visualization libraries. And out of all these, you might have seen that Jupyter is a constant, it helps you do interactive data science. So there's no open source alternative in the Python land. So there were certain challenges with Jupyter, like you might have also faced it. Like a lot of times, the sessions crash, the notebook become unresponsive. And then if you are using it on a cloud environment, like how scalable it is, how many users can you fit on a single machine to reduce cloud costs, and then the user experience part and the packaging part. So enter Jasper. So Jasper is a high-performance IDE for Jupyter notebooks, and it's how it is better in performance. Is that it uses 5x lesser CPU than Jupyter Lab and 40x lesser RAM than Jupyter Lab. It is even faster, and it has ultra-low latency, and the kernel startup time is much faster, and it has higher throughput. So yeah, we have 14K users and around the world. So yeah, let's go into the architecture. So whenever you launch a Jupyter notebook or an IDE, you get options to create different types of notebooks. So when you create a notebook, a kernel is spun up. Like let's say you launch a Python notebook, and a Python kernel spuns up in the background, and and a connection is made between the Python kernel and the backend, and these communicate together, and that's how the computation happens. So this diagram shows how it works. So in the center, you can see there's a Go backend with a React frontend. The user interacts with the React frontend. The message goes to the Go backend, and the communication happens with the Python kernel. And how this, Jasper is in a separate process, and these Python kernels are in a separate process. And how these two processes communicate is via 0MQ. So, and how does this communication happen between these two processes? Now, this diagram explains it in detail. For example, I have tried to make it look like a WhatsApp chat, like if a user interacts with an IPython kernel, what happens? Now, let's say I type a command 2 plus 2. The answer should be 4, right? So you send an execute request 2 plus 2, and then you get multiple messages like status busy, and then what is the type of the request, and what is the result, and then the final status. So when you see these 4 channels, like in the image on the left, like these are control channels, cell channel, IOPub, and STDIN and heartbeat. So think of these channels as like wires. Let's say in a normal wire, like in our appliances, we have a wire with 3 different wires combined together. Similarly, think of these as 5 different wires, and this is where the message flows. So now I'll show you a demo. So yeah, this is how the IDE looks when you start it. And for example, on this screen, you can see there's multiple kinds of kernels. And there's a terminal. So first start the terminal, and it's a normal one, like ls, it worked. Then I'll go to a Python kernel. I select the type of kernel, and it's launched. When you see the green button, that means the kernel has started. Now I start executing. Okay. So you can run NumPy, then pandas. I am rapidly executing all these codes. And yeah, pandas. Pandas is for data frames. Then we have this matplot. So matplotlib is for visualization. So for example, in this case, I'm using a random array and trying to plot it. So you can see that the graph will change every time because the new random array gets created all the time. So you can see, plus if anyone has used Jupyter already, they might be noticing like how fast it is. So yeah. And the thing that how fast, if I can, the kernel startup time, let's say this is the line number 26, and I wanted to show this behaves real time. I click on this reload, and everything will run just, okay. Yeah, so this is the speed, like 26 cells, rerun all things all at a time. So this is what the speed I'm talking about in Jasper, and like which uses Go in its core. Now coming, okay, one more thing I had to show you. So this also supports Go kernel and Ruby kernel. I will show you how it works in Ruby. I just say puts hi, and yeah. So yeah, so it supports all kind of kernels, like even JavaScript kernel, and yeah. Okay. Now coming back to the internals. Now this is like the meaty part, like why you like the geeky part, like why how I built that. So between two processes, I need to make them communicate. I could have used something like REST or something else, but in this case, we are using 0MQ. 0MQ is a library that helps you communicate over sockets. Plus, it also gives you a way to create message queues. So like when two sockets are talking to each other, no message is missed. For example, let's say there's a client, there's a server. They both start talking to each other, like they both are connected on the socket. One goes down, like if let's say client says ping, and the server it goes down. So in that case, the message will be lost, right? But in case of when you're using 0MQ, this message is stored. Like when the server comes up again, it again binds to that socket. That ping is received, and the server can again respond with a pong. So this is how 0MQ works. So 0MQ is also like it helps you build chatty systems. Like this is the core library that is being used in for fetching ticker data, like in the stock markets. So yeah, and 0MQ allows you to create fan out, pub sub, plus like task distribution, request reply, all kinds of those patterns. So yeah, you can basically create a P2P, a peer-to-peer client for downloading torrents or something like Skynet, so something like that. So now the thing is, when I built this in Go, the major thing was like why there is a major performance gain. So this all boils down to async IO versus Go routines. In Python, we have something called asynchronous IO, which helps you do things concurrently. So how are these two different? Like one used by the Python and one used by the Go. So Python has lightweight, Go has lightweight green threads, whereas async IO has all those thread-bound, single-threaded coroutines. So what happens is, like all these, let's say there are multiple coroutines that were scheduled in a Python. So all of them will be using a single thread, and they have to be cooperatives to work together. But in Go, when these Go routines are created, they can be you run on multiple threads. Like if you have an 8-core CPU and each CPU has one thread, then you can use all those 8 threads together. And I think the last talk explained much in a very cool way, like how those threads are scheduled on by the Go scheduler. Next thing is like the scheduling is by in Go, the scheduling is by Go runtime scheduler, but in Python we have the event loop. And event loop is a much different architecture compared to the Go one. Next is the blocking behavior. In Go routines, the routines can block, but in asynchronous IO, they must not block, and you have to use async and await very properly to make this work. Now, coming to the syntax, like people generally think, like I used to think that Go would be a much very tough language, but in compares to when you are building coroutines or like you want to achieve concurrency, Go is much easier to build and implement compared to Python. Like Python, you will have a lot of issues regarding garbage collection, then the threads will not wait, and then the IO loop might crash. So all these things. So this is the code comparison. Like if you had to subscribe to a socket, like I said, no, IPython kernel, and you have to talk to this socket. You have to write code at multiple places. Like in Jupyter, we have it in Jupyter Client, Jupyter Server, and then you have to build your own, write your own class for achieving this reactor kind of mechanism. When the message goes in, like for example, if I send 2+2 execute request, it has to bind to a, like it is a future and it has to bind to a callback. So when that future is resolved, that callback has to execute. So yeah, so this is much tougher to implement. And how we do it in Go? Simple. We just run a loop, and then before that, you can call a Go routine, and then just communicate by channels. So yeah. So now let's run some benchmarks on this. So this benchmarks will cover like this is, let's say I build this, and I can't say, trust me, bro, it's much faster. We do a proper set of like load testing and find out that what is the speed, how much RAM is consumed, how much CPU is consumed. So let's say when I created, like when I showed you in the demo, I was opening various notebooks. So these are various sessions. So for each sessions, we will have multiple, we have one IPython kernel opened. So this is a session. So I'll try to, in this benchmark, I'll try to create multiple sessions at a time. And for each session, like each session will be running in a coroutine, and I'll signal all of them that, hey, start sending message on all of these. So like you are concurrently sending messages in parallel to on all those sessions, and then each Python kernel will start replying back, and then we will try to see that if messages are lost or not. So this is something like like if you are trying to build a load testing in your own, for your own project, you can use this as an example. So and then yeah, and once we do this, we also monitor that how much RAM is being used, how much CPU is being used. So all of that. Okay. So yeah, I am something of a data scientist myself. I'll try to be as much this should be backed by science, so that it should be very repeatable experiment. So one thing, like we as a system, like people who build, like if you are building a large system, you must be able to measure this RPS, or we try to measure with requests per second or messages per second. So what we are trying to do is we try to calculate the message sent throughput. Like this is equal to the number of kernels into requests sent per kernel. In simple terms, so like if I have created a session and I create 10 notebooks, and on each notebook I am sending 20 messages per second. So at overall we are sending for 10 notebooks into 20, 200 messages. So that is the message sent throughput. Now message received throughput, like every time you send a message, you get 5 messages back. For example, I showed you, if I send 2 plus 2 and then I get 5 messages back. So this is the return throughput. So 5 into 200 is like 1000. So if that number, like the received throughput starts dropping, this means something bad is happening with the system, like the kernels are not responding. So like if you see a Jupyter notebook being crashing or it's unresponsive, this is because it becomes unresponsive. So we have to make sure that this sent through, like the received throughput should not go down. So here are the results. Like once I run this is the, like this is the result. So in the orange line is the represents Jupyter, whereas the blue one represents Jasper. So the first one is the CPU one. So CPU usage is always constantly higher. While for Jasper, it is much lesser. And for the RAM, you can see that RAM is consistently low, like it's a constant line. But for Jupyter, it's much higher. Same, the third diagram, the third and fourth is about the send throughput and received throughput. So send throughput, received throughput, like both are at the same point, like you can see. So this means no, like the performance is same, like no messages are being, all the messages are being received properly, no kernel misbehaved, and then, but the CPU and RAM is much lower in case of Jasper. Now this one is for uh, 64 kernels. That one was for 2 kernels. This one is for 64 kernels. For 64 kernels, again, we see that the CPU and RAM usage is lower. But in case of message received throughput, like the fourth diagram, you can see that the Jupyter has, the messages received are much lesser. So that means your kernels are dying. So kernel crashes happen. And so, so yeah, you can't handle much kernel. Next is for 100 kernels. For 100 kernels, you can see that the 4 diagram, the message received throughput crashes completely. It goes to 0. That means for 100 kernels, Jupyter Lab will not survive at all, but Jasper continuously keeps running and it maintains the throughput. And for the RAM also, like for Jasper, it's continuously much constant, but for Jupyter, it jumps and then it starts to crash. So, yeah. And this is the overall summary for the CPU usage and RAM usage. For CPU usage, this is Jasper increase linearly. Jupyter also increases, but at last for 100 kernels, it starts to drop because like the Jupyter has crashed, Jupyter Lab has crashed. Same thing for, next is for RAM. The RAM usage is much less in terms of Jasper, but for Jupyter Lab, it goes high. So kaboom, we have built the best notebook ID in the market right now. So nothing even come closest to it. Thank you. Is my time up? Okay. So why is
When I hear claps, I come on stage. Sorry.
okay. Why is Jasper outperforms Jupyter Server? So we can effectively use multiple cores with help of Go. Then Go's model is much closer to the hardware. And then Python has a GIL. And right now they have introduced experimental way for getting losing GIL, but still let's see. But yeah, and then fourth is the garbage collector. Garbage collector is something like which we, like for any highly scalable application we are building, if there's a lot of garbage and when the GC kicks in, it makes the matter worse. So that's why Jasper was like, it was properly maintained, the garbage collection as well. So we didn't have much issues, but Python, it suffers even because of a GC. So try for yourself. This is an open source framework. Like you have an ID is an open source, and this benchmarking is also open source. How is the diagram? Okay, other PyData tools, okay, what does this mean of using Go? So yeah, Go is basically helps you to build something which is cloud native. So Jasper takes care of that. For individual user using Jasper is like, you get much improved responsiveness and like much lightweight. And for enterprises, you get cost and efficiency and better scalability. And other PyData tools that may leverage Go are like Bokeh and Dask, which follow a similar way, like you have a distributed compute, and then most of these communicate via Tornado and this asynchronous I/O. This is the road ahead. So like we are going to support different notebook formats, plus improve the UI components, and then build more intelligence into it. Plus add S3 object storage for sharing, and then also add data apps, plus Jasper Hub. So yeah. I'd like to acknowledge FOSS United and Zerodha for supporting this project with a grant. And that's all. Thanks.